All right, so today we're going to continue our discussion of putting energy to work, and we're going to look at heat engines, which is something that we're going to look at a lot in this course. Our basic definition of heat engine is loosely defined as any system that turns heat or thermal energy into mechanical energy, something that we can use. And here from the text is a couple different examples of this. Probably the most useful for us be number 3, which is a car engine, the abrupt temperature increase in an internal combustion cylinder that drives a rapid expansion of gas within the cylinder, which then can be used to turn something around, making the wheels turn. And then steam in a power plant races through a turbine because it is flowing to the cold condenser. That's basically a description of a power plant. And so we're going to look at the model that describes all of these things, but with sort of a special emphasis on 3 and 4. Here's the cartoon picture of how a heat engine works. So a heat engine will have a hot reservoir that's kept at a temperature TH and a cold reservoir kept at a temperature TC. And basically we take heat, which is delta QH, so delta QH, out of the hot reservoir. We use some of it for work, and then the rest of it is expelled into the cold reservoir. So this is just this equation right here. This equation is simply just conservation of energy. The amount of energy we take out in heat from the hot reservoir, we then use some of that for work, and then whatever is left over, we have to expel it into the cold reservoir. So we're going to go through and kind of look at how this works. And just to let you know where we're going, this is our equation that's going to be sort of our key equation, which is the maximum efficiency for this engine. And so we'll sort of show how we get there. And just kind of a little picture, that cartoon picture is nice and it's going to be useful, but this is just how this might work in real life. And so a basic heat engine, we heat water into steam. That's done right here. And so that's adding heat from the hot reservoir, the heat source, into this water. The water is heated up and the steam does work, typically spinning a turbine that spins an electric generator, creating electricity to use in our homes. Then the steam cools down in what's called a condenser using a cold water source that's at temperature TC, which then basically absorbs this heat QC so that the water can come back down to the original temperature and start the whole thing over again. So that's your basic picture of a heat engine. Now, some definitions here. Now, heat engine, sort of an important concept to a heat engine is something called entropy. And unfortunately, we don't have time to get into this, all the way. But I think just talking about it a little bit is kind of nice. And so entropy, the technical definition is a measure of how many ways a system, might be organized at the microscopic level while preserving the same internal energy. Now, what we're going to use, and this is by no means a perfect way to think about it, but it can be useful, I think, is entropy as a measure of disorder. And so basically, if you look at disorder, the more disordered something is, we're going to sort of look at that as having a higher entropy. Now, this doesn't work in all cases, but I think it can be a good rule of thumb. And so basically, disorder is just things that are kind of random and all over the place. And so when things are more disordered, we generally think of that as a higher entropy. So the two rules that are going to define our heat engines are called the first law of thermodynamics and the second law. The first law is just conservation of energy, right? It's just saying that whatever energy we take from the hot reservoir has to equal the work plus the heat we send into the cold reservoir, like we were just talking about. Now, the second law, which is important, is the second law of thermodynamics. And this says that the total entropy of a closed system may never decrease. And what does that say? Well, that basically says that, things don't get more ordered by themselves, right? If it's a closed system, it's either going to stay the same level of disorder or have that disorder possibly increase. It's not going to sort of magically get more disordered. And one way to kind of to look at this too is this idea of the arrow of time. And so this thing from the book asks you to look at videos of a rock splashing into water or a coffee mug shattering on the floor. When you watch a video of something like this happen, you know which way the video should be going, right? If you do it in reverse, it looks really weird. And this is a good example of what we're talking about here. So there's situations that don't violate the first law. They don't violate conservation of energy, but they do violate the second law. An example of that would be the coffee mug. If you look at the coffee mug, right, conservation of energy works. The energy of the coffee mug before as you drop it and after as it shatters, if you look at all the pieces, the energy would be the same. And so there's no reason that we couldn't do that movie backwards and have, that work backwards according to just conservation of energy. However, entropy would be violated. This idea of the mug sort of jumping up and randomly forming that order, right, sort of getting more ordered out of disorder without anything happening from outside is again, not possible. And so it would sort of, it would be really so these more ordered states are less likely to spontaneously emerge as this thing shows. And so it's really clear which one is sort of the right way to run these videos. But again, it's important that, we're not violating conservation of energy there. We're just violating the second law, that the total entropy of a system may never decrease. Now, when we're doing this in practice here, we're going to use this equation here. So this is our equation for entropy change. And so when energy is moved into or out to some thermal bath, like we've been talking about, you're going to have a change in entropy, delta S. And it obeys this relation here, that delta Q is equal to T times delta S. And so what this says is when heat is removed, the entropy is reduced. And hopefully that makes sense. If you have some system and you take heat out of it, the system is going to kind of slow down, become more ordered. Right. The opposite, if heat is added, entropy increases and it gets more disordered. One note here is that in this here, temperature must be in Kelvin. And so here, Kelvin, as we've mentioned, is just the centigrade temperature plus 273. So it's not a tough thing to do, but it's easy to forget. So just try to keep that in mind. And so when we have a heat engine, the total entropy is going to be the entropy change for the cold reservoir and the entropy change for the hot reservoir. The hot one is negative, right, because it's losing heat, and so it decreases its entropy. It gets more ordered. The cold reservoir has heat added to it, so it gets more disordered. And according to the second law of thermodynamics, the total entropy change has to either be greater than or equal to 0. And so if I take this and sort of bring this guy to the other side, I get this relationship here. This idea of delta SC is greater than or equal to delta SH. And I can just do one former step a little bit further and write it out like this here. So according to the second law of thermodynamics, the entropy change in the cold reservoir divided by the entropy change of the hot reservoir has to be greater than or equal to 1. All right, and so now we can go through, and over here I'm just going to write this equation. So this again is our conservation of energy that we have, and I'm also going to write it this way here, and so just solve for the delta W, the work done. And it looks something kind of like this here. And so we're going to find the efficiency of our heat engine this way here. And hopefully this makes sense. And so what this is, it's basically the benefit we get, the delta W, divided by what we have to bring in to get that benefit. So the heat we're bringing from the hot reservoir, like in that case of a power plant, we have to keep some fire going, burning coal or something, to heat up that water to do that work. And so it's the benefit we get divided by the cost. And what we can do is, for this work, is plug in these two guys, delta QH minus delta QC, just from over here, divided by delta QH. And what I'm going to do now is just write this in terms of its entropy and the temperature. So I get sort of like something like this here. And again, this is in the book, so just trying to kind of discuss this a little bit more in depth. And so I'm going to divide both sides by 1 divided by delta SH. And what that does, it'll cancel out the SH on the bottom and then bring in an extra piece on this term. So it'll be like this, delta SCH, and then down here like so. So this is the efficiency. And what we just talked about is that this ratio of delta SC over delta SH has to be greater than or equal to 1. And you're going to find out that this efficiency will be its biggest when this ratio is exactly equal to 1. And if you go through and you can actually try having it be greater than 1 and show that it actually gets to be smaller. And so this is our, again, maximum efficiency for a heat engine. So a couple things of consequence from that. So first, any temperature difference can be exploited to generate mechanical energy. And so that's sort of the name of the game. People have been trying to use any temperature difference they have to make mechanical energy and devise better engines. The greater the temperature difference, the more efficient the engine. And then energy waste is inevitable. Now it is possible that if TC is 0 to have a 100% efficient engine. But of course that would be, because this is the Kelvin scale, this would be a temperature of negative 273 degrees centigrade, which doesn't exist on Earth. So on Earth it's practically impossible. All right, so let's look at some examples. And so let's just look at a sort of regulation, sort of typical coal power plant. How efficient is that? And so a coal fire burning at 552 degrees Celsius delivers heat energy to a reservoir at 27 degrees Celsius. Now, the trick here is that, again, we need to put this into Kelvin. And so my temperature hot is going to be 552 degrees Celsius plus this number 273. And so my hot temperature, when I write it out that way, comes out to be 825 degrees Kelvin. And then the cold temperature is this 27 degrees Celsius plus 273, which is 300. So now just because it's a nice round number, typically we'll use TC for, just environments on the Earth. 27 is higher than room temperature, but again, this kind of works for most environments. So that's what we'll tend to use. Okay, so then we're ready to do this. So the energy max is just going to be, again, TH minus TC divided by TH. So I get 825 minus 300 Kelvin, all divided by 825 Kelvin. And when I did this, I got about 64% efficient. And so what that means is, again, similar to that coffee cup, technically, by conservation of energy, you should be able to take all the heat out of the hot reservoir and turn it all into work. But unfortunately, this second law of thermodynamics, the entropy, actually puts a limit on what you can do. And so no matter how good you are at building a coal fire power plant, it's going to come out, the best you can do is 64% efficiency. You're going to end up having to waste some energy. So again, just like this, we're saying this point right here, energy waste is inevitable. In this case, 64%. Here's a chart looking at sort of the development of electrical power plants over the years. And so when they first started, it was really not very efficient. It was less than 10% efficient. And nowadays, so we're basically in the range of 30 to 40%. So, again, for a coal power plant, 64% is your maximum. And then what it does, it becomes an engineering problem. And so basically, even with that, they can only reach a portion of that. You can't do sort of 100%, the maximum efficiency. All right, let's do some more examples. So here, if a heat engine is observed to remove 30 joules from the hot bath and deposit 20 joules into the cold bath, what is the efficiency of this heat engine in producing useful work? And so this is one that gets back to sort of our definition. So again, what is our definition? Well, if we use conservation of energy, our heat engine works like this. We take some heat from the hot reservoir, and then that heat, basically we do two things with it. We try to do as much work as we can, again, to produce electricity or make the car go faster, whatever it is, and then we're going to end up expelling some. And so here, the 30 joules is going to be the QH, and then 20 joules will be the QC. And so from that we can figure out, well, what's our delta work going to be? That's going to be 10 joules. Okay, and so then what is our efficiency? Well, again, it's this formula, but what it really is it's basically how much work do I get, divided by sort of how much energy am I taking out of that reservoir, right? So I mean, again, the hope would be you want to maximize the amount of work as close to that heat that you're taking out of the reservoir as you can. Again, there's a limit, but you want to do the best you can. And so here it would be 10 joules divided by 30, and so that gives us an efficiency of 0.333 repeating, which is a 1/3, which is basically 33% or roughly. And so in that case there, your engine is efficiency of 33%. All right, our last example here, an automobile engine has an efficiency of 22% and produces 2,510 joules of work. How much heat is rejected into the cold reservoir by the engine? So if you want, go ahead and pause, give this a try, and then we'll come back and talk about it. All right, so again, our efficiency is our work divided by the heat that we took out of the hot reservoir. Now, in this problem, we've got two of these variables. We know how much work is done, and we know the efficiency. So I'm going to take this equation. So the efficiency is 22% or 0.22, and that equals the work, which is 2510 joules divided by QH. And to be consistent, I should put a delta down here. And so I can solve for this QH, and when I get that, I get about 11,400 joules. Now, so you might want to pick A, but again, this is the heat that we're taking out of the hot reservoir. The question's asking how much heat is rejected by the engine, which would be delta QC. And so delta QH equals delta work plus delta QC. And so again, we know sort of two of these, so I'll write 400 joules. The work there is 2510 joules plus delta QC. And when I went through and solved for this, I got, again, roughly 8,900 joules. All right, so this is, again, this equation will be really important to us as we're going to spend a lot of time looking at heat engines, power plants, this sort of thing.